we're mostly going to start by talking about isotopes here. I'm actually going to go back a little bit further. I'm going to remind you that atoms have 3 subatomic particles associated with them. All atoms have what? Absolutely must have a proton, at least one proton. Electrons, numbers of electrons, which are the what charged particle? Negatively charged particles. The protons are positive. Electrons can be gained and lost in chemical reactions. So the number of electrons can definitely move around a bit. Also, whether an atom truly possesses an electron or not is kind of philosophically difficult to answer sometimes. For example, what kind of bonds do we get when atoms share electrons? What's that? When they share, what do we call that kind of bonding? It's covalent. Sometimes they're polar, which means one atom is it's selfish. It's not sharing very well. So ultimately, it gets controversial when we start saying how many electrons does an atom have in a compound. But when we talk about a neutral compound, you'll recall, first of all, how do we figure out how many protons an atom has? Very easy. You just look it up on the periodic table. Good. So for example, zinc has 30 protons. Why does it clearly not have 65.38? Why is that not possibly going to be the answer? Because the number of protons must be a whole number, right? Can't have 65.38 protons. So you should never make the mistake of mixing those numbers up. Every element has a unique number of protons, correct? So if I know that an element has 6 protons, what's the only element I could possibly be talking about looking at the periodic table? Carbon, right? Is there another 6 by itself anywhere on the table? No, nor will there ever be. Okay, so we already know about atoms having protons. Atoms are our fundamental unit here. If an atom is neutral, meaning it has no charge, what must we say about the number of protons and the number of electrons? They are equal. Good. And again, I'm treating this as a review because you all learned that, right? Number of protons and number of electrons are equal. What if an atom has gained or lost electrons? It now has a thing called charge. And what do we call atoms with charge? Ions. Very good. Okay. If an atom has gained or lost electrons, it is now charged. What do we call it if it's positively charged? A cation. Good. And if it's negatively charged? An anion. Good. So we remember all that. Okay. We call those monatomic ions, meaning what? They are just the one ion by itself, as opposed to what I was showing you on the screen a moment ago, the polyatomic ions. Can you name a polyatomic ion for me? Ion? What's that? Acetate, good. Chlorate, nitrate, bromate. Yeah, all of those are polyatomic ions, which means they have many ions, and somewhere they gained or lost electrons. Do we know who took them away? No. Or who gave them to them? No, it's not relevant. Okay. So the protons and the electrons are probably the easiest particles to understand. Proton is positive, the electron is negative. Many atoms, but certainly not all atoms, also have a neutral particle, at least one of them, and those are called neutrons, okay? There are many atoms. In fact, almost half the atoms in the universe don't have neutrons, and that's because the element hydrogen often doesn't have them. All the other elements, to my knowledge, at least those that occur naturally, have at least one neutron. Sometimes, who knows, you might be on Jeopardy. What element doesn't have neutrons a lot of the times? Hydrogen, okay? It just doesn't. Now, so the number of protons, we already talked about that, is the atomic number, and we're going to usually use the letter capital Z for that. That comes up a few times this semester, that capital Z, and we won't ever see Z being anything else. So hydrogen atom always has 1 proton, Z equals 1. Helium always has 2, Z equals 2. As I said, an uncharged atom always has the same number of electrons as protons. On the notes, where are we here? This is page number 12. Is that right? Okay. Oops. Congratulations. We're now on page 79. All right, let me go back. Sorry about that. My computer is being a little wacko here. Good. Okay. Where do the protons and the neutrons, if an atom have them, live? They live in the nucleus. Good. So if I showed a picture of an atom, it would look something maybe like this. This area in the center is the nucleus. It has any protons and any neutrons that the atom happens to have. Where are the electrons? They are somewhere surrounding the atom, we will say in the outer region. What is an electron? Good. Is it a particle? Is it? Maybe it isn't. Chapter 7, we'll find out. Okay, but for right now, let's keep life easy. Protons and neutrons are particles in the nucleus. Electrons, we won't even say what they are. They're particles that are a little bit like waves too. Float around the atom. Do they go in nice little circles? Nope, not really, no. Okay, but again, that's all way off chapter 7. We'll get to that. What do we call atoms with the same number of protons but different numbers of neutrons? We call those isotopes. Very good. Okay. Now let's start with probably the weirdest case, and that's hydrogen. Hydrogen atoms. If I randomly go through nature, if I randomly grab a water molecule is going to have how many hydrogens in it? Two. And I look at those hydrogen atoms, the vast majority of those hydrogen atoms have no neutrons. Occasionally, though, I run into a hydrogen atom that does have a neutron. So how can they both be hydrogen? Well, because they both have a proton. And that's the only definition for an element as to how we name it, the number of protons. So if two different atoms have the same number of protons but different number of neutrons, we call them isotopes. Iso usually means what? You'll see iso a lot. Isotopes, isomers. Iso means really the same, okay? So same something or other, okay? So hydrogen is rather strange in this respect. Its isotopes get special names. We just call hydrogen with 1 proton and 0 neutrons, we just call it hydrogen. But if you're talking specifically about isotopes, hydrogen with 1 proton and 1 neutron gets the name deuterium. And it gets its own special symbol, D. Is it on the periodic table? It is not. It's here somewhere, okay? There's the D in there somewhere, I don't know, anyway. But it doesn't actually physically appear on the periodic table. Sorry, I skipped something. Let me go back and get that and come back to deuterium in just a moment. The mass number is the number of protons plus the number of neutrons. And we use the letter A to symbolize that. So the way we name the isotopes is we just say the name of the element and then the mass number. So hydrogen with 1 proton and no neutrons would be called hydrogen 1. Technically. Hydrogen with 1 proton and 1 neutron would be called hydrogen 2. As I said, it gets a special name, deuterium. You probably don't need to memorize that, okay? Hydrogen with 3, what would that be? How many protons in hydrogen 3? Always 1. If I say the word hydrogen, you always know 1 proton. So that would be 2 neutrons, is called tritium. It's also radioactive. Okay. Carbon is another one that we see, that we deal with the isotopes a lot. No other element, to my knowledge, gets special names. So carbon with 6 protons and 6 neutrons is called carbon 12. 6 plus 6. Carbon with 7 neutrons is carbon 13. Carbon 14 is 6 protons and 8 neutrons. What's special about carbon 14? Besides being radioactive, what is it used to do? Anyone know? You're in the right area. It's used in a process called carbon dating, which is not a romantic interaction, okay? Carbon dating is used for establishing how old something is because it gives off radiation at a predictable rate. And you can look at the rate of radiation being given off and say, I think this is 2,000 years old versus I think this is 5,000 years old. It's got limits. It's got uncertainty like all measurements, but that's where you've probably heard of it if you have heard of carbon 14. Okay. All right. The symbols that we use for this looks like this. Now, in the notes, I think I have an error here. There's an N. I don't know how that N got there, but that should be an A over a Z times X. So, although we're really never going to use that letter A again outside of this chapter. So this should be an A, excuse me. So the way we symbolize elements is like this, although we can technically leave out Z. X stands for the symbol. So for example, carbon 13 can be written like this, or it can be written like this. Why can we leave out the 6? Yeah, it's redundant. If there's a C, then that means it must have a 6. Anyone know why we do this weird system? You don't need to know this, but so I wouldn't write this down or it'll confuse you. But let's say we had carbon 14 and it eliminates a beta particle. This is a new kind of reaction that you will not learn about until Chem 140, called a nuclear reaction. All the reactions in chemistry don't involve the nucleus. They involve what particles? Electrons. Good, right? They share or lose electrons. But as you will learn in chapter 19, if an atom like carbon decides to expel a beta particle is a high energy electron. You have to balance nuclear equations. And so the way the rules work is the top number has to be the same. They have to add up to the same thing on the left and the right. And the bottom number has to add up to the left and the right here. So in order for this to work, if this is 14, 14 is 0 plus what? 14 is 0 plus 14, very good. And 6 is -1 plus 7. What element would this have to be? If that's a 7, this must be nitrogen. Good. So elements can't change in chemical reactions, but they can change in nuclear reactions. Good. So if a carbon expels a beta particle, which is a high energy electron, it becomes a nitrogen atom. Yeah. Really cool stuff. This electron didn't exist. It suddenly was created in the nuclear reaction. It got spit out and it went and did some damage somewhere. Anyway, that's not something we have to worry about in this class. But now, if you were ever wondering, why is this so stupid? Why didn't they just write number of neutrons? Because that always annoyed me. It's like, why didn't they just write 8 there? Because you can't do nuclear equations unless you do it this way. And so now if you were wondering, why do they have such an odd system? That's why we have such an odd system. I now want you to forget nuclear reactions even exist, okay? Push them into the back of your mind until next semester, if I teach it, because I'm the only one who does. None of the other professors think they're important enough. Anyway, sorry. Are we going to do nuclear reactions at Rio Hondo? Well, you're doing them right now. You're all hitting each other with carbon-12. You're all doing that to each other. You can start packing up. I'm just babbling at this point. But no, we do not have a nuclear reactor at Rio Hondo.
Yes.
What?
Yes.
Yeah. UCI, when I was there as a graduate student, they did have a nuclear reactor in their basement, but they had to get rid of it because the professor who was using it was no longer using it, and keeping a nuclear reactor around is generally not a safe thing to do. Okay, it was a very, very tiny nuclear reactor. All right, guys, I will see you all on Thursday. If you have any questions, please come see me now. Don't forget though, if you have lab, don't talk to me for too long. You have to go to lab. All right.
They're getting new chairs.
They're there yet. Not in that room.
Not yet.
No, they're all sitting right there on the opposite side of the wall, and we have to assemble them.
It's a fun project.
So when my back is feeling good, I will hopefully go in on Friday and maybe build them for you. Okay? But no promises. Okay, I'm going to go ahead and end the recording at this point.